Okay, so these are really easy to solve. They might just look a little weird at first. So what you're actually trying to solve for is this value right here. You're just trying to figure out what it is. So if you know the rate, you'll notice that's this term. So if you know the rate, and if you know your A term, then you can go ahead and you can figure out the relationship between the rate and the n. Now, K is a constant, and what that means is it's a unique to that reaction, so it's reaction specific, but it's a constant. So it doesn't matter at what concentrations that you run it at, this is always going to be constant, and so it doesn't matter that much. So I'm going to set it mathematically, but you can also think about it, just think about it, and it makes sense too. So here's what we're going to do. We're just going to pick a set. So I'm going to pick like this one and I don't know, like this one. So I'm going to pick those two and just random. Like any set you pick should always give you the same answer. There is a hint is to put the large number on top. So we're going to actually be putting things in as a fraction. Notice that this is the large number and that's his matching number. So that's what we're going to put on top. So if this is the rate law for one of the reactions, when we want to figure out what is the exponent, what we're going to do is we're just going to set one rate or one series of reactions equal to the other. So you just say 2.6 times 10 to the minus 2, and you're going to see me filling all of this in, K, 0.9 raised to the n. And then that's just, I just picked rate for the reaction 2. Now I'm going to put reaction 1 in there. I just randomly had picked that one. And so here's reaction 1, 0.866 times 10 to the minus 2. I'm still the same K because it's the same reaction. It's reaction specific, constant throughout. 0.3 to the n. All right, so first of all, these two terms cancel. And you might be able to see the math just by filling it in. But I'm going to go ahead and add it in, or divide. So 2.6 e to the negative 2. Oops. Clear. 2.6 e to the minus 2 divided by 0.866. E to the minus 2. And so that gives me 3, and I know there's a little decimal place in there, but there's an awful lot of 3 in there, okay? And then you might be able to do this when you're ahead. 0.9 divided by 0.3 is also 3. But we have the exponent here. It's 3 raised to the n. Because with exponents, you can combine things like this. That is the same thing as when you have it for each of them. So 3 to the n. So now you tell me what n is. This is raised to the 1 because there's nothing there, so it has to be raised to the 1. So n is equal to 1. So this is going to be a first order reaction. Now, could you have figured that out yourself? Probably. So if you had, like just by inspection, if you had looked at the 9 to the 3, you probably looked and saw that's a change of 3. And then if you look here, you might not have been sure what the change is, but you might have been able to guess, or at least ask yourself, is that a change of 3? And actually, I guess I put this in as a third. I should have done the arrow this way. This is a change of 3, right? And then let's see if this is a change of 3. So 0.866 times 3, 2.6. Yeah, that is a change of 3. So when they change in the same way, so if you triple something, it triples the rate. If you double something and it doubles the rate. If you quadruple something and it quadruples the rate. If the rate is doing the same thing, then it's first order. So that's what we have over here. So don't let the fact that this is a change of 3 make you think that the exponent should be 3. That's not what it means. You have to compare the two of them together. But the math is perfectly fine to do it. Again, my big key point, I'm going to work the second one, is to pick a larger, and this time I'm going to do this set here and this set here. Pick the larger set to put on top. It'll make it so you don't have like exponents sitting on the bottom and stuff. It just always makes the math easier. So in this case, the rate is 0.2 over 0.1 equals, there's a K and a K, and then my 0.2 rate is 1, and my 0.1 rate is 0.25. And notice that these are both raised to n. My k's cancel out. You can probably see that I have 2 times. Now 1 divided by 25, or 0.25, is 4 raised to the n. Now you can go ahead and do the log and everything, or you might see that 2 raised to the 1, it's the same thing as saying 2 raised to the 2 times n. 2 raised to the 1 is equal to 2 to the 2n. So what we're saying is that in this case, n is equal to 2. So when you double the concentration, you quadruple the rate. When you double the concentration, you quadruple the rate. So do you see how the rates aren't doing the same thing? That's how it works.